In this video, we'll be covering empirical formula, and we've reviewed this in class, but just to make sure we're clear on what the notes should say. First thing you're going to do, if you have a percentage empirical formula, which we will see a problem about this, you're going to change your percentages that are given into grams. And the easiest way to do that is you have a 100-gram sample of the substance. Therefore, if one of your elements were 30%, for example, it would be 30 grams. Percent meaning per 100. After that, you would convert those grams to moles. This is for all stoichiometry. Units to moles, units to moles, units to moles is probably the most important thing you need to remember. Now, we will look on another set of problems about combustion. That's going to be a little bit different, but primarily what you're going to focus on is changing grams to moles for your substances, or for the atoms or elements that compose your substance. Then you're going to find the moles of elements that are in the original sample. Now, this is more relevant to combustion. If you're doing something where you're trying to find the carbon that was in carbon dioxide or the hydrogen that was in water, we will look at that problem in the next video, which will deal with empirical formula and combustion. You may find that one of your products is missing some mass, or your total sample might be missing some mass. That'll also be more relevant with the combustion samples we'll see in the next video, but just so that we're aware that these are all of the steps. If you do not need to check for missing mass, you're going to move on to the step 5. And if you do need to check for missing mass, primarily with combustion and oxygen, then you're going to have to change your moles of carbon and hydrogen or nitrogen back to grams in order to find what mass you might be missing from oxygen, for example. Then you're going to divide the smallest number of moles, divide each of your numbers that you get, each of your mole values, divide it by the smallest number of moles in order to find an empirical formula, which is the smallest whole number ratio of atoms in a substance. If your mole quantities are not close to whole numbers, you may need to multiply all of these quantities by the same increments. We will see a problem like this coming up in this particular activity, in this particular video. And if the sum of the molar masses does not equal the molar mass, you're going to have to multiply until it fits. I will show this also, what this actually means. The challenge with empirical formula and stoichiometry is the more you do it, the better you get. Memorizing rules is not necessarily the most helpful, though I did present them here. It can help you walk your way through a problem, but the real help, the real assistance that I can provide on this is leading you through problems and figuring them out. So the first one is percent composition, and we do see that there is one value that will make sense a little bit later, and I forgot to put an animation on that one. So a compound is found to contain 63.52% iron and 36.48% sulfur. Find its empirical formula. As I said in my previous slide, we want to work with a mass that's easy to change from percentages to the grams. And the best way to do that, if I had a 100-gram sample of my iron and sulfur compound, then 100 grams would be the best way to manage that, because in that particular case, 63.52% of 100 grams would be 63.52 grams, and 36.48 grams would be 36.48 grams. 36.48%, would be 36.48 grams. Makes your job a lot easier to get to a 100-gram sample from percentages. Does it need to be 100 grams? No, but that's by far the easiest conversion that you can make. From there, as I've said before, units to moles, units to moles, units to moles. Moles are the common currency in chemistry. It's one of the most important concepts, which is why we're going to see it a lot. It's really essential in order to determine your yields, or determine the number of reactants you need, or determine how much product you should be producing. You're going to have to get very comfortable with mole conversions. So in this particular case, I take my 63.52 grams of iron, I change it into moles by multiplying by 1 mole over 55.8 grams, or it's the same thing as dividing by the gram molar mass. The only reason I set it up this way is so that we are sure we're canceling out the units we do not want, we're keeping the units we do want, and I get 1.14 mole. Now this, by now you might be able to guess, this is the gram molar mass of sulfur. And in this case, I have 36.48 grams of sulfur times 1 mole over 32.06 grams. Again, I'm canceling out my units. At the same time, I'm just basically taking 36.48 grams and dividing it by the gram molar mass of sulfur to find out how many moles of sulfur I have. And already you can tell this is a ratio that's very easy to determine. If it's 1.14 to 1.14, that is the same thing as 1 to 1. And that would mean that my empirical formula would be 1 iron to 1 sulfur, or iron 2 sulfide. Do not forget how to name things. Iron and sulfide make an ionic compound. Sulfide has a -2 charge. In order to balance that -2 charge in a stable compound, I need a +2 charge on the iron. And that's how I know this is iron 2 sulfide. Now this one is actually a little bit easier because we have a sample of a substance that contains 1.05 grams of nickel and 0.29 grams of oxygen. So in this case, I actually don't have to go from percentages to grams. I already have 2 perfectly good gram values. And from those 2 perfectly good gram values, now I want to find the empirical formula. Again, first step, units to moles. We've done this before. So 1.05 grams of nickel, and then I multiply that by 1 mole over the gram molar mass. Basically, I'm dividing the grams of nickel by the gram molar mass, but I'm leaving the units that I want at the top. So I have moles. I do the same thing with oxygen, basically dividing the grams of oxygen I have by the gram molar mass of oxygen, and I get 0.018, 0.018. Again, this is another very simple problem. I just wanted you to be familiar with the idea that in this case, the grams do not need to be changed into percentages in this particular case. Again, I'm going to divide by the lowest number. In this case, both of the lowest number. So I get 1 to 1. This is my 1 to 1 ratio, which means the chemical formula is nickel 2 oxide, very similar to iron 2 oxide. But remember, what does this actually mean? There is no molecule of nickel 2 oxide. The 2, for one thing, refers to the charge on the nickel ion. Oxide has a -2. In order to have a stable compound, nickel has to be +2. But in no case are we finding 1 nickel joined to 1 oxide in the compound. This is a chemical representation of nickel 2 oxide. What do I see? I see a nickel ion, an oxide ion, a nickel oxide. The ratio 1 to 1 to, the ratio is always at its simplest a 1 to 1 ratio. For every 1 nickel, I have 1 oxide. So nickel oxide, nickel 2 oxide. But in this particular case, we see that the real actual ionic compound has many, many ions in it. But don't ever get confused that the 2 in any way has anything to do with the number of atoms, because it doesn't. Nickel 2, the 2 refers to the charge on the nickel 2 ion, which it needs to be a +2 in order to balance out the oxide's -2. Because in any stable compound, in any formula unit, in any molecule, in this case we're referring to a formula unit, the charges must be balanced in your actual sample. So this is why -2, +2, and the nickel 2, that number 2 comes from the charge on the nickel ion. Okay, now we're going to level up a little bit. Here we're dealing with a molecular formula. Your first step is still going to be an empirical formula, but you will need to do one additional step in order to get to a molecular formula. So this is a molecular formula with a compound that is a mass of 180 grams. This tells me that the 0 is significant. But that is not important right now. I do not know what my compound is, so I really can't do anything with this number at the moment. What I can do something with is 91.38 grams of carbon, 15.38 grams of hydrogen, and 121.74 grams of oxygen. My total sample is a 228.50 gram sample. Again, I don't know what the compound is, so I can't do anything with that at the moment. But what I can focus on are my carbon, hydrogen, and oxygen, and change each of them from grams to moles. So in that particular calculation, same thing. Grams of carbon, gram molar mass of carbon, I get 7.61 moles of carbon. I get 15.23 moles of hydrogen. Again, in this case, 15.3 grams of hydrogen times 1 mole over 1.01 grams. That's the gram molar mass for hydrogen. And therefore, I get 15.23. And the last one is 121.74 grams of oxygen divided by the gram molar mass of oxygen. Now, I have had a question from certain students about why is this not H2? Because this hydrogen and this oxygen are not in their free elemental state. These are in a compound. So O2 does not occur in a compound. Hydrogen, H2, does not occur in a compound. They only occur as elements in nature, which in this particular case, both of these are in compounds, so I only need to divide by their gram molar mass that I would see in the periodic table. It's only when they're in a gas form as a pure element that I see H2 and O2. In no other case would I see those two atoms joined up in that manner. So from there, I'm going to follow the same algorithm I've been doing. Divide by the lowest number, which means 7.61 gets divided by 7.61. I get 1, I get 2, I get 1. That means that my empirical formula is 1 carbon, 2 hydrogens, 1 oxygen. Now, if you really knew your organic, you might remember that this CH2O is the same molecular formula for formaldehyde. But as you'll see, if I actually add it up from the empirical formula, if I added up a molar mass, that would be 1 carbon plus 2 hydrogens plus 1 oxygen, gives me 30 grams per mole, which would be the correct the correct molar mass for formaldehyde, not the correct molar mass for this particular substance, because as it says, we ran this through a mass spectrometer, and the molar mass is 180 grams, not 30 grams. So now I have to figure out what factor do I need to multiply all of these numbers by in order to get up to a 180 grams. The ratio needs to stay the same. So if I multiply this by 2, I need to multiply that by 2, I need to multiply that by 2. So it would mean if I multiplied everything by 2, C2H4O2 gives me the same ratio as CH2O. But we're very confident in this case the empirical formula cannot be the same as the molecular formula. Therefore, we're going to divide the molar mass that we're given by the empirical mass, which gives me a factor of 6, which means all of my values here need to be multiplied by 6, which means that my molecular formula is C6H12O6, which you may recognize as glucose. Now, here's one additional challenge. This is where it gets a little bit more, or we add one more step. It's not as more complicated. We just add one more step. In our original presentation of what the rules are for empirical formula, I said we had to have the possibility we have to multiply ratios until whole, which you will actually see in this particular sample. So again, molar mass for this particular compound is 118. Can I do anything with that at the moment? No. What can I work with? I can work with 1.715 grams of carbon, 0.5047 grams of hydrogen, and the remainder being nitrogen. So be aware of that. From this point, I can move ahead with changing carbon, units of carbon to moles of carbon. So grams of carbon to moles of carbon. We've done that many times before. Grams of hydrogen to moles of hydrogen. We've done that before. Now, what do I do about the nitrogen? I'm given that I have a 4.22 gram sample of nitrogen. I know that that sample contains 1.715 grams of carbon and 0.5047 grams of hydrogen. So if I had I know there are no other elements in this particular compound, which means I add this to this. I add my total mass of carbon to the total mass of hydrogen to my total mass of nitrogen, and I should get 4.22, which is my total mass. So if I plug in my values, this is basically my X value. I'd subtract both of these from 4.22 in order to find that my mass of nitrogen is 2.00 grams. Now I know my grams of carbon, my grams of hydrogen, and my grams of nitrogen that were in that original sample. Now I multiply this by 1 mole over 14.01 grams, the gram molar mass of nitrogen. Remember, this is nitrogen in a compound. In a compound, it will not occur as N2, and in a compound, I only need to worry about nitrogen and the gram molar mass of nitrogen, and I get that value. Okay, next step is dividing by the smallest. We've seen this before. So that's a 1, that's a 1. These are pretty clear. 0.143 divided by 0.143 equals 1. This one, however, comes out to a 3.5. Now, if you remember, empirical formula means smallest whole number ratio. I do not have a whole number here. What I'm going to do is I'm going to have to multiply each of these by the same value in order to get this to become a whole number, which in that particular case is going to be a 2. 1 times 2 is 2. 2 times 2 is 2 down here. 1 times 2 is 2. 1 times 2 is 2. That's no surprise. 3.5, I got a little ahead of myself, my apologies. 3.5 times 2 is now 7. So my empirical formula will be C2, because I'm dealing with carbon, C2, H7, and then N2, C2H7N2. That is my empirical formula, where it says in my original rules, multiply until whole. I have to multiply, in this case, everything by 2 in order to get a 7. If this were a 3.25, then I might have to multiply by a 4. But in this case, 3.5 times 2 gives me 7. That is not the final answer, however, because my molar mass is 118 grams per mole. And I got to insert another animation here. But the empirical formula is C2H7O2, as we established. The molar mass would therefore be 2 times 12 for the carbons, 7 times 1 for the hydrogens, 2 times 14 for the nitrogens, to give me a total of 59 grams per mole. If the actual molar mass is 118 grams, I divide that by 59, I get a 2. That means my multiplying factor here is 2. So I have to multiply carbon by 2, hydrogen by 2, and nitrogen by 2. And my molecular formula for this particular compound would be C4H14N4. And if I had 4 times 12, which is 48, plus 14 times 1, which is 14, plus 4 times 14, which is 56, I believe, off the top of my head, I'm thinking. The total mass should be 118 grams.